So to prove triangles are congruent, we have SSS, SAS, ASA, AAS, and now this one, which is sort of the stranger at the family reunion, it's HL when we have right triangles. So let me show you what I mean. The hypotenuse-leg congruence says, if the hypotenuse and leg of a right triangle are congruent to the hypotenuse and the corresponding leg of another right triangle, then the triangles are congruent. Now usually we see something like this and we see, well, we've got an angle and a side and this other side, but the angle is not the included angle. And so we talked about how side-side angle does not work. So hypotenuse leg is that one special situation where if the angle is a right angle, then we form a right triangle. And therefore this is one way for that to work out. So we can prove that triangles are congruent using HL. So we still have three requirements for an HL proof. Even though we only have H and L, we still have three requirements. The first requirement, we need to establish that the hypotenuses are congruent. Secondly, establish that both of the corresponding legs are congruent. And finally, we need to establish that both triangles are right triangles. Now the typical way that this is established is the fact that we'd have two right angles in a box above, and then the definition of a right triangle says that if we have right angles in a triangle, then that creates right triangles. So that would establish right triangle HL proof. Using HL can be a bit confusing. So for example, here we have two HL or potentially SAS proofs. In the first example, here we've got our angle, and then the two sides indicate that the angle is not included. In other words, it's not in between the two angles. And so, this would indeed be an HL proof. This next example, we see that the angle is the included angle. In other words, the angle that we know something about is in between the two sides that we know something about. And so therefore, this would be a side angle side proof. It's going to be important to keep these straight. In this first example, we're given that angle B and angle R are both right angles, and we're also given that segment BN is congruent to segment AR. And our job is to prove that angle NAB is congruent to angle ANR. So in order to do that, we first need to establish that these two triangles are congruent, this triangle and that triangle. So the blue angles, we've got two right angles, which indicate either that we have right triangles or that we've got congruent angles. We've got the two red segments, and then we've got this shared side up the middle. And so in this case, we actually have an HL proof. And here's why. We're given that these are two right triangles. The hypotenuses are congruent because that's a shared side, and then these two corresponding legs are congruent. And so we're going to use HL for this proof. So we know we're going to set it up with three boxes funneling down into one. The order in which we fill these boxes doesn't matter, but I'm going to start with the hypotenuses. Okay, just kidding. I'm going to start with the two legs. We were given that segment BN was congruent to segment AR. And so those establish our congruent legs. Now we don't have to show that these are congruent legs. I just wanted to indicate that they are congruent legs for you. Next, we want to establish that the hypotenuses of our two right triangles are congruent, and so we have that shared side NA, and so the reflexive property guarantees that NA is congruent to AN. And then finally, we need to establish that we have two right triangles. Since both B and R are right angles, The definition of a right triangle says that these two triangles, BAN and RNA, must also be right triangles. And so now we've established that those two triangles, BAN and RNA, are congruent. Now remember, we were trying to prove something about segment lengths. No, pardon, about angle measurements. And so once we've established that these two triangles are congruent, we can then use the CPCTC to say that those two angles, the corresponding angles NAB and ANR, are congruent as well. And so there we go, we're done with that proof. In this next example, our goal is to prove that this segment, PR, is congruent to SR. In order to accomplish that, we'll first need to prove that these two triangles are congruent. So let's examine the given information. We know that PQ, segment PQ, is congruent to segment ST. Next we have the statement that says that PS is a perpendicular bisector of QT. So this is kind of a two-for-one statement. First we have that PS is perpendicular to QT, and so that establishes that these two angles are right angles. And we also have that PS is a bisector of QT. In other words, QT is being bisected, and PS is doing the bisecting. So if QT is being bisected, that means that QT is the segment that's cut in half. And so now we have enough evidence for an HL proof, because we have these black hypotenuses, these blue legs, and these two red right angles indicate that we have two right triangles. So let's build our HL proof. First we have given that segment PQ is congruent to ST, and so we have our hypotenuses congruent. Next, that dual statement, PS is a perpendicular bisector, gives us both that PS bisects QT and PS is perpendicular to QT. And so using the bisector part, we get that QR is congruent to RT. And so that establishes that the two legs of the right triangles are congruent. Next, the fact that we have perpendicular segments means that we have right angles. So angle QRP and angle TRS are both right angles. And the fact that we have right angles in triangles, that indicates that we have right triangles, based on the right triangle definition. That triangle QRP is congruent to TRS, and by the CPCTC, we've established that PR is congruent to SR. And we're done. As an interesting thought experiment, if instead of the hypotenuse is congruent, we actually knew that the two legs, the two pairs of legs were congruent, then we would have evidence for an SAS proof. So again, it's important to keep those two straight. So if that were the case, then we'd use SAS, but in that previous example, we used HL. In this last example, our goal is to prove that angle 3 is congruent to angle 4. Now once again, we're going to prove that by proving that these two triangles are congruent first. So let's examine the given information. We know that NP is a perpendicular bisector of MO. And so perpendicular bisector, again, we get 2 for 1. NP is perpendicular to MO, which means that we've got two right angles. Also, we've got a bisector. Now, MO is being bisected, and NP is doing the bisecting. So since MO is cut in half, that means that MP is congruent to OP. Now, we're out of given information, but we do have this shared side up the middle. And so in order to prove that these two triangles are congruent, we're actually going to use SAS here. Right? We don't know anything about these hypotenuses, but we do know something about these two congruent sides and the included angles, the right angles. So we'll use SAS. So here we have, off to the left, we've got the shared side, which gives us that NP is congruent to NP. Next we've got those congruent angles, MPN and OPN, based on the fact that we had perpendicular segments. And then finally, we've got the fact that NP bisects MO, which gives us that MP is congruent to OP, which is true by the segment bisector definition. And so now we've established that our two triangles are congruent, and so using the CP-CTC, we now prove that angle 3 must be congruent to angle 4, because they're corresponding parts in congruent triangles.